Hello. This presentation is for my final project for computational math. Um, we have two problems. We'll start with problem number one. First, I'll change this to show all code. Okay, problem one. Using R, generate a random variable x that has 10,000 random uniform numbers from 1 to n, where n can be any number of your choosing greater than or equal to 6. Then generate a random variable y that has a 10,000 random normal numbers with a mean of mu equals sigma equals n plus 1 divided by 2. So first, we're going to generate the random variable x, and is from 6 to 100, so it's greater than 6. And I picked 100 so that we have a certain amount of numbers. And then we have 10,000 trials. When we run the code, we'll see it's a uniform uniform numbers. Excuse me. Then we generate a random variable y. The mean is n plus 1 divided by 2, and the standard deviation is the same, n plus 1 divided by 2. We have 10,000 number of trials, and we create a random variable y with the normal numbers. So we have a bunch of probability questions. Calculate as a minimum the below probabilities A through C. Assume the smaller letter x is estimated as the median of the big X variable, and the small letter y is estimated as the first quartile of the y variable. Interpret the meanings of the probabilities. So x is median of small x is median of big X, small y is the first quartile of big Y. So the first probability is probability of x is greater than median of x, given that x is greater than first quartile of y. So let's calculate the median of x and assign that to the small x. Let's find the first quartile of big Y and assign that to small y. And what we need to do, we need to find the probability of big X greater than small x and big X greater than yx, and divide that in by probability of big X bigger than y. So big X, the probability of big X bigger than small x and big X bigger than small y is sum of all the possibilities where x is bigger than small x and big X is bigger than small y. And then we divide that all the possibilities for x. And for probability of x bigger than y, it's sum of all the possibilities where big X is bigger than small y, and then we divide that by all the possibilities for x. So I did that here, and I assigned them to P1, P2, P3 objects. So P1 is basically the sum of all possibilities where x and P1 is basically probability of x bigger than small x and x bigger than small y. P2 is x bigger than small y, and P3 is the answer of our question, which is the probability of big X bigger than small x, given that big X bigger than small y. This means the probability of big X being greater than X's median, given X being greater than Y's quartile for first quartile is 60%. The B is another probability question. The probability of X is greater than all possible median of X, and Y is greater than all possible quantile of Y. Which is basically sum of all the possibilities where X is bigger than small x and Y is bigger than small y, and we divide that with all the possibility of X, which we did here. So this means probability of X being greater than median of big X and Y being greater than first quartile of Y is 37%. The C, the question is probability of bigger X smaller than probability of X is smaller than median of X, and X is greater than first quartile of Y. So sum of all the possibilities where big X is smaller than small x, and big X is bigger than small y. and divide that by all the possibility of the x will give us the probability. So this means the probability of x being smaller than median of x and x being greater than first quartile of y is 34%. In this task, we're being asked to investigate whether the probability of a big X being greater than small x and big Y being greater than small y equals to probability of big X being bigger than small x multiplied by probability of big Y being greater than small y. And we've been asked to build a table and evaluate the marginal joint probability. So what I did here is I created all the possibilities where x is bigger than x and y is bigger than y and all the different variations, and I assigned them values of a, b, c, d. Then I created objects that are totals of a plus c, b plus d, a plus b, b, c plus d, and then also the totals of the last two. And then I created objects to, if I divide them by the number of trials, is going to give me the probabilities of each single one of them. So I created all of those and assigned them here as objects. Then I created the table and I assigned the row and column names. And here we are. When we look at here, if you look at x bigger than y, x bigger than x, small x, and y bigger than small y, we see the value here equals to the probability is x bigger than x and y x big X bigger than small x and big Y bigger than small y. And we see approximately the values are the same, so there's independence. It meets the condition, the condition that we're investigating. In this task, we're asking dependence, Fisher's exact test, and chi-square test. So check to see if independence holds both. Holds by using Fisher's exact test and chi-square test. What is the difference between the two, which is most appropriate? So when I created this, I didn't create the matrix, so I did that in here. It's a 2x2 matrix. Then I just applied the function Fisher.test, and I see the p-value. I did the same thing for chi-test, chi-square test, and I get the same p-value. Basically, we use the Fisher's exact test if the sample size is small, I think less than 5. In this case, our sample size we have 10,000 trials, so we recommend to use the chi-square test. So that completes the problem 1. So we move to problem 2. So in this problem, I already had an account in Kaggle. And it's in regard to the house prices competition. First thing I did was to load the train and test data sets. I always look at the first 5 columns. I did that for both. The first 5 rows, I did that for both. And I always add the variable definition. I thought it was going to be much more helpful. There's 80 something of them, but I added them here anyway. Sometimes I refer back to those. The first question we have is descriptive and inferential statistics. Provide univariate descriptive statistics and appropriate plot for the training data set. Provide a scatter plot matrix for at least 2 of the independent variables and independent variable. Derive a correlation matrix for any 3 quantitative variables in the data set. Test the hypothesis that the correlation between each pairwise set of a variable is 0 and provide an 80% confidence interval. Discuss the meaning of your analysis. Would you worry about formula-wise error? Why or why not? So first, I look at the structure. I see 1,459 observations and 81 variables. They're all different types, integer and categorical variables. I look at the summary. This is the descriptive statistics. I'm able to see for the numerical variables, I'm able to see the minimum, first quartile, median, mean, third quartile, and maximum numbers. Then I wanted to look in detail on neighborhood, sale price, house style, and overall condition variables. So the average lot area in the data set is 10,517 square feet. Maximum lot size is 215,245 square feet. Average sale price in the data set is 180,944. The maximum sale price is 755,000. And I did some visualizations around to see the distribution. It's not necessarily a normal distribution for, but I guess it's close for the sale price variable. I looked at the house style. The majority of the data has the 1-story and 2-story houses, depending also within neighborhoods. I looked at the overall condition of the house. Has a positive correlation with the sales price. The median of, for example, if the overall condition is high, the median of the sale price is a lot higher. And I looked at the neighborhoods, and we can see the sale price is higher depending on certain neighborhoods. Scatter matrix correlation. Then I selected the variables, the feature sets that I thought would be helpful with the analysis. I call them the DF-train1. I did the same thing for test because I wanted to use the select function, and if I load the mass library, it depreciates the select function, which I'm going to need to load that library later on, so I just did it in here. So I have the test and train sets with certain features identified here. I created the correlation matrix by using all the variables within the train 1 dataset from the variables I selected from here. So this gives us an overview of the correlation between, for example, sale price and overall quality. Gives us an overview of the correlation. I did a scatter plot just to look at the correlation specifically for overall quality and sale price. Then in terms of hypothesis, the correlation between each pairwise set of variable is 0 is our hypothesis. The confidence interval is 80%, so I look at the p-value of each variable and with the 80% confidence level. So first I look at the sale price versus overall quality. I see the p-value is low. I see we are 80% confident that there's 78 to 80% correlation between sale price and overall quality. I did the same thing for sale price versus year built. If the p-value is low, so there's definitely correlation between the sale price and year built. We are 80% confident that there's a 50 to 55% correlation between sale price and year built. I did the same thing for sale price for lot area. We're definitely sure that there's a correlation between them, and we're 80% confident that 23 to 30% correlation between these two variables. This disgusting meaning is basically what I just explained. 80% confident that with low PO, there's a correlation between these variables. The next section is linear algebra and correlation. Invert your correlation matrix that we created above. This is known as the precision matrix and contains various inflation factors on the diagonal. Multiply the correlation matrix by the precision matrix, and then multiply the precision matrix by the correlation matrix and conduct a lower and upper triangle decomposition on the matrix. Invert your correlation matrix from above. So I think I'm supposed to load this later, but somehow it got here. But anyway, I created the precision matrix. I already had the correlation matrix, so this is the precision matrix. Then I did the multiplication requested. So, and I assigned them objects mult1 and mult2. You can see them here. In terms of the LU decomposition on the matrix, I know in the past assignments we created our own functions. I used matrix calculator library. In this case, it has a function called lu.decomposition. So I did that in here. The next task is calculus-based probability and statistics. So we're assigned to select a variable from the training data set that we've been working on. It's skewed to the right, shifted so that the minimum value is absolutely above zero if necessary. Then load the mass, which we already did. Find the optimal value of lambda for this distribution, and then take 1,000 samples from this exponential distribution using this value, plot a histogram and compare it with the original variable using the probability distribution. Find the fifth percentiles using the cumulative distribution function. Also generate a 95 percentile confidence interval from the empirical data, assuming normality. Finally, provide the empirical 5th percentile and 95th percentile of the data. So first I selected lot area, and I used the fit distr function for the exponential distribution. Then I created the optimal value for the lambda, and then I took the 1,000 samples and created distribution and simulated distribution here with the histogram for the exponential distribution. And then I did the histogram for the original variable. It's more of a normal distribution. So I'm not sure if there was another variable that could have been better than lot area, but I think it's still pretty decent. I broke this to 50 so that we can see the exponential distribution. Find the 5th and 95th percentiles using the cumulative distribution function. I did that. I generated 95% interval from the empirical data. So this is the mean, somewhere in here, and then this is the normal distribution. I put the mean and the standard deviation, and I broke it down into 100 so we can see it. Finally, provide the empirical 5th percentile and 95th percentile of the data. I did the same thing in here. And these are the numbers. Modeling. Build some type of multiple regression model and submit your model to the competition board. Provide your complete model summary and results with analysis. Report your kaggle.com username and score. So we have the training data set. I always look at it for some reason. Here is an overview. I created the model. I selected sale price as the target variable, and then we have lot area, year built, overall condition, and overall quality as the feature variables, as the explanatory variables. And we can see that p-value is low. And when we look at the residuals, we see that it's normally distributed. I created a function to see if we want to eliminate any of the variables to have a better model, but I decided to keep all the variables within the model. I got the AIC and BIC numbers, and then finally I did the prediction, and I submitted to Kaggle, and I got the 0.87%, 87.1 score. Obviously we can do a better model. We can add categorical variables, like the neighborhood seems to be an important variable, and use random add like a random forest or some decision tree um, to get a better model for prediction. Um, and this concludes my final project for the computational math class. Thank you.